Imagine a metal so rare that most people don't even know it exists. It's not gold, it's not platinum, in fact it's much more obscure. This metal hides at the very end of the periodic table's rare earth series, and has the name that sounds straight out of a fantasy novel. Yet despite its anonymity, it plays a vital role in modern technology and even in life-saving medical treatments. Meet lutetium, an unsung hero of the periodic table, a rare earth metal that's quietly saving lives, and you probably never heard of it. Welcome to Cube Chemistry, where we will discuss all the elements of the periodic table and also do experiments. Now if you like these videos and want to see more, make sure to like, subscribe and hit the notification bell so you will never have to miss another episode. Also fill in the poll in the post section of the channel so you can influence next week's element. Now, since we came back to the Lanthanides, it will not surprise you that this is another silvery grey metal. It is a solid at room temperature, but it looks indeed a lot like the other Lanthanides. Now, since its appearance is not that interesting, let's head it back to the question, can you lick it? Using the periodic table that we will, like mentioned, rewrite at some point in the future, it states, go for it. So yes, you can. It is safe to do so, since lutetium is not considered highly toxic. It doesn't react aggressively with your body the way something like mercury or lead might. Brief contact, like touching or licking, isn't going to cause any harm as long as the metal is clean. But even if that would be the case, we, as always, would not recommend you to do so. Now, if you want to collect lutetium or other elements like we do, click on the link in the description, use the promo code, get a 10% discount, and you will also be helping out our channel. Now, the story of lutetium begins in the early 20th century amid a flurry of scientific discoveries. At that time, chemists were racing to identify the last unknown elements lurking in a group called the rare earth metals, a collection of metals that were notoriously difficult to tell apart. In 1907, Georges Urbain, a French chemist, and Karl Auer von Welsbach, an Austrian scientist, independently found evidence of a new element while analyzing a substance called ytterbia. And we've discussed this before. Now, ytterbia was thought to be pure ytterbium oxide, but it turned out to be a mixed bag containing an undiscovered element. Now, each scientist claimed credit, and each proposed a different name for this new metal. Urbain, proud of his Parisian heritage, chose the name Lutetium, after Lutetia, the ancient Roman name for Paris. Welsbach, gazing at the night sky for inspiration, suggested Cassiopeium, after the constellation Cassiopeia. So the stage was set for a scientific naming showdown. For a couple of years, academic sparks flew. Urbain and Welsbach each insisted that they had been the first, and even accused each other of using the other's result. It was like an early 1900s version of a Twitter feud. Yeah, I'm using Twitter because an X feud just sounds weird, albeit conducted through scholarly letters and papers. Now finally, in 1909, an international chemistry committee weighed in to settle the matters. They examined the evidence and concluded that Urbain deserved the credit. The committee officially adopted lutetium as the element's name, honoring Urbain's discovery and his beloved city of Paris. Lutetium literally means out of Lutetia, essentially Parisian metal. It's as if Urbain said, I'm naming this one after my hometown. Welsbach fans weren't pleased. In fact, German scientists stubbornly clung to Welsbach's name, Cassiopeium, for decades. For a long time, if you studied chemistry in Berlin or Vienna, you might see element 71 listed as Cassiopeium, CP, instead of lutetium, LU. It wasn't until the 1950s that the name lutetium, with a slight spelling change from lutetium, won out everywhere, and Cassiopeium faded into history. The naming drama gives lutetium a unique legacy. It's an element named after an ancient name of Paris, thanks to a determined French chemist. So, lutetium is essentially the Paris metal. Ironically, Paris is nicknamed the City of Light. And as we will soon discover, lutetium has a lot to do with lightning and vision in modern tech. A fitting twist for an element named after the City of Light. Lutetium holds a special place on the periodic table as the last member of the Lanthanide series. The rare earth elements. If you've ever looked at that separate block of 15 metals usually shown at the bottom of the periodic table, lutetium is the one at the very end. Atomic number 71. Now, being last comes with a few bragging rights. Lutetium is the densest, hardest, and high melting of the rare earth metals. In other words, among the rare earth cousins, lutetium is the tough one. It's heavier, more stubborn about melting than the rest. Now, this silvery gray metal has a high melting point of about 1652 degrees Celsius or 3025 degrees Fahrenheit, and that's hotter than a blast furnace and the highest melting point in its family. It's also quite dense, packing nearly 9.8 grams per cubic centimeter, close to 10 times the density of water. If you held a chunk of lutetium in your hand, not that most of us will ever get the chance to do so, more on this rarity soon, it would feel surprisingly hefty for its size. Now, despite being literally tough and heavy, chemically lutetium is a typical rare earth metal. That means it's reactive, but not outrageously so. In air, a piece of lutetium metal will slowly tarnish as it reacts with oxygen. It forms a dull oxide layer over time, however, it is not as quick to corrode as some of its lanthanides neighbors. Now, if heated, lutetium metal burns with a bright white flame to form lutetium oxide. In plain water, lutetium reacts only slowly. Room temperature water doesn't bother it much, but hot water will get it fizzing as it generates hydrogen gas. And like most metals, if you drop lutetium into acid, it will dissolve. In fact, dilute acids will readily eat away at lutetium, turning it into solutions of lutetium salts. One funny exception, hydrofluoric acid, barely touches it, because lutetium quickly forms a protective layer of lutetium fluoride. That stops the reaction, almost like an invisible Teflon coat. In compounds, lutetium is almost always found in the +3 oxide states, meaning each lutetium atom likes to give up 3 electrons to form chemical bonds. As a result, lutetium salts like lutetium chloride, nitrate, or sulfate, etc., tend to be colorless or white. They don't show off bright colors the way that some transition metals do. Why? Because lutetium electrons are all tucked away in filled shells. It has a full 4f electron shell, which doesn't interact much with light. In fact, lutetium's electron configuration is so complete, often written like this, that chemists sometimes quibble about whether lutetium should be considered a lanthanide at all. All the other lanthanides have partly filled 4f shells, but lutetium 4f shell is full, and it only has 1 electron in the 5d shell to do chemistry with. This has led to some playful argue that lutetium is an honorary transition metal, hanging out with the lanthanides but not quite one of them. It is a little bit of a nerdy debate. Rest assured, lutetium is usually counted as a rare earth element, but it certainly has its own personality at the party. Another interesting tidbit, lutetium is paramagnetic at everyday temperatures, meaning if you put it near a strong magnet, it will be weakly attracted, but it's not permanently magnetic itself. And if you cool lutetium near the absolute zero and squeeze it under extremely high pressure, it even becomes a superconductor, conducting electricity with zero resistance. But only under very extreme conditions that are more a physics lab curiosity than anything practical. We've been calling lutetium a rare earth, and it lives up to the name. In fact, lutetium is one of the rarest of the rare earth elements. It's not completely non-existent. The Earth crust does contain lutetium, but only in tiny concentration. On average, you would find on the order of 0.5 milligram of lutetium in a kilogram of ordinary rock. To put that into perspective, imagine a huge 1-ton boulder. That big rock might contain just about 0.5 gram of lutetium at most. Lutetium is even less common than precious metals like gold or platinum in the Earth's crust. So if you thought platinum was exclusive, lutetium is an even more elite club of scarcity. What's more, lutetium never occurs by itself in nature. There's no lutetium mine or rich lutetium vein lurking underground. Instead, lutetium atoms are always mixed in with other chemically similar elements, usually other rare earths. Mother Nature essentially hid lutetium inside the same minerals where other rare earth metals reside. Over the 19th and the 20th century, chemists discovered a whole parade of these rare earth elements by chemically teasing them apart from certain exotic minerals. Lutetium was the last of these to be separated because it was buried in a mix present in such tiny amounts. So, where is lutetium found? Well, the classic sources of rare earths are minerals like monazite or bastanaazite. These are rare earth-rich ores mined for more common rare earths like cerium, neodymium, or yttrium. Lutetium is a minor ingredient in those ores. For example, in monazite sand, which is mined in places like Brazil, India, or parts of Africa, lutetium might make up only 0.0001% of the material. That is a mere trace. Picture extracting one part out of a million parts. Other minerals like xenotime, a phosphate of yttrium, and euxenite, a complex oxide mineral, also contain lutetium in small proportions. In recent decades, a lot of heavy rare earth elements, including lutetium, have been obtained from ion absorption clays found in southern China and other locations. These clays are soils that, through eons of weathering, became rich in heavy rare earths. Miners can literally dissolve these clays with weak acid to collect rare earth elements. Now, lutetium is one of the heavy rare earths, and while it's still on the tiny fraction of those clays, at least the clay is easier to process than rock-hard minerals. Today, the main producers of lutetium as part of rare earth mixes are places like China, which dominate the rare earth market, along with smaller contributors from countries such as Myanmar, the United States, Brazil, India, and Australia. Now, the world production of lutetium, usually extracted as lutetium oxide, is extremely small, on the order of 10 tons per year or so. 10 tons! That's about the weight of a single school bus, spread across the whole planet annually. No wonder you don't see lutetium in everyday life. It's literally one of the least common elements we've ever get our hands on. Now, how do we go from lutetium hidden in ore to pure metal? Well, the process is a testament to chemical perseverance. First, the ore, like monazite, has to be broken down, typically digested in hot concentrated acid. This dissolves all the rare earth elements into a solution. Early on, chemists found that adding certain chemicals would cause some elements to precipitate out, while others stayed dissolved. For example, in processing monazite, thorium, another element present, can be removed by making it form an insoluble sludge, thorium hydroxide. The remaining solution still contains a cocktail of rare earth ions, including lutetium. By adding other reagents, chemists convert the rare earth into forms like oxalates, which precipitate, and then heat those to get rare earth oxides. Even then, all the rare earths are still mixed together in that oxide powder. Imagine a grab bag of lanthanide oxides. The trick to separating lutetium from all the others is to exploit tiny differences in solubility or preference for certain solvents. One historical method was fractional crystallization, where you dissolve the mixed oxides in acid, then carefully crystallize out compounds like double salts. Lutetium tends to crystallize out a bit differently than the others, if conditions are just right. But the method could require hundreds of repetitive crystallizations, an absolute nightmare in terms of time and effort. It's no surprise that Charles James, the American chemist who also worked on lutetium's discovery, was famous for patiently performing countless of crystallizations to purify rare earths. He reportedly had the world's largest supply of lutetium at the time, simply because he kept at separation process relentlessly, while others squabbled over naming. Now, modern methods are kinder, relying on ion exchange columns and solvent extraction techniques. Ion exchange, a solution of mixed rare earths, is passed through a special resin that grabs onto the metal ions. By washing the column with careful chosen solutions, scientists can make different elements let go at different times. Lutetium, being one of the smallest lanthanide ions, can be coaxed out after the others, yielding a relatively pure lutetium solution. In solvent extraction, the mixed solution is shaken with an organic solvent containing chemical ligands that prefer certain lanthanides over others. By repeating many stages of this extraction, elements can be isolated. Think of it like a huge bowl of nearly identical beads by color. You may need many rounds of sorting to get the pure color out. Lutetium is the tiniest bead among the lanthanides, which gives it slightly different behavior that skilled chemists exploit. Finally, once lutetium is in a purified compound, often lutetium chloride or fluoride, the last step is to obtain the metal itself. The result? Tiny amounts of pure lutetium metal ready for use. It wasn't until 1953 that chemists were able to produce pure lutetium metal in appreciable quantity, which shows just how challenging the task is. Extracting it is like finding a needle in a haystack, using chemistry as our magnet. Given this effort, you might wonder, what do we actually use this elusive element for? Why go through all of this trouble? Well, as it turned out, lutetium, although hiding in the shadows, has some remarkable uses that make it well worth the hunt. Now, because lutetium is so rare and costly, you won't find it in bulk uses or consumer products in any significant quantity. Instead, it shines in a handful of highly specialized applications where its particular properties are uniquely valuable. One such role is as a catalyst in chemical and petroleum industries. A catalyst is like a chemical matchmaker. It helps reactions go faster or occur under easier conditions, without being consumed itself. Lutetium oxide and other lutetium compounds have been found to be effective catalysts for certain reactions. Now, for example, in oil refineries, lutetium-containing catalysts can help in cracking processes, breaking down large hydrocarbon molecules into gasoline and other useful fuels. They've also been investigated for the use in alkylation, rearranging molecules to improve fuel quality, and making in various polymers, plastics. Now, you might ask, why use lutetium if it's so expensive? Now, the answer is that the catalysts don't use much lutetium, often just a tiny amount on larger support. And in some cases, they might offer an efficiency or a selectivity boost that cheaper metals can provide. Still, because of the cost, lutetium catalysts are a niche. Another technological area where lutetium makes an appearance is advanced optics and electronics manufacturing. Lutetium's garnet compound, lutetium aluminum garnet, is a superstar in disguise. Now, this synthetic crystal has a very high refractive index and excellent transparency. In fact, lutetium-based garnet crystals have been proposed for use in immersion lithography, a cutting-edge technique used to make microchips. In immersion lithography, manufacturers shine lasers through a crystal lens system to etch incredibly fine details on silicon chips. A lutetium aluminum garnet lens could potentially focus light better due to its optical properties, enabling even smaller feature sizes on future chips. In simpler terms, lutetium could help make more powerful computer chips by improving the way we focus light during their production. It is pretty wild to think that an element no one ever talks about might be quietly pushing the limits of Moore's law. Speaking of lasers, lutetium is making waves there too. Certain laser crystals based on lutetium compounds, for example, lutetium aluminum garnet, can be doped with other rare earth ions like ytterbium, thulium, or holmium to create efficient solid-state lasers. Now, researchers found that lutetium in the host crystal can improve laser performance. It's physically robust and can handle high energies. These lasers operate in the infrared and are used in applications ranging from medical procedures to military rangefinders. Now, let's shed some light on a more everyday application, lighting itself. If you have an LED light bulb at home, those energy-efficient light bulbs that are everywhere right now, you might indirectly be using a dash of lutetium. White LED bulbs actually start out with a blue or ultraviolet LED and then use phosphor materials to convert some of that light into other colors, resulting in white light. Now, one phosphor used in high-quality white LEDs is lutetium aluminum garnet, doped with cerium. This phosphor emits a broad spectrum of yellowish light when excited by a blue LED, and when combined with the blue light, it produces a pleasing white glow. Lutetium also takes on an X-ray vision role, or more precisely, it helps detect X-rays. Compounds like lutetium tantalate are used in X-ray phosphorescent detectors. Lutetium tantalate holds the title of the densest known white solid. It's extremely good at absorbing high-energy radiation, like X-rays, and then re-emitting the energy as visible light. Now, this makes it ideal for screens or detectors in X-ray machines. When X-ray hit the lutetium-based phosphor screen, it glows, creating the image we need for medical or security imaging. Because it's so dense, it can stop X-rays effectively, meaning clearer images at lower doses. Now, beyond this, lutetium finds use in some scientific instruments and research. Geologists, for example, appreciate lutetium's long-lived radioactive isotope, lutetium-176. They use the lutetium hafnium dating method to determine the age of ancient rocks and meteorites. Lutetium-176 decays very slowly into hafnium-176 over billions of years, so the ratio of lutetium to hafnium in a sample can reveal its age. It's a bit like a geological clock hidden in crystals. And speaking of clocks, in the realm of cutting-edge physics, lutetium atomic clocks are an area of research. So let's talk about the medicine where we use it. Now, here is where lutetium truly earns the tagline saving lives. While the pure metal and its stable compounds find only niche uses, one of lutetium's isotopes have become a more rising star in the fight against cancer. This is lutetium-177, a radioactive form of lutetium that has proven to be a powerful tool in nuclear medicine. Lutetium-177, often written like this, is produced by bombarding a stable lutetium or ytterbium isotope with neutrons in a nuclear reactor. Talk about high-tech alchemy. The result is a lutetium atom that emits beta particles and gamma rays, with half-life of about 6.7 days. Now, in plain language, lutetium-177 gives off a type of radiation that can destroy cells, but it only remains radioactive for a short period, roughly a week, with half the radioactivity gone. This combination, relatively low energy beta radiation and convenient half-life, makes it near perfect for certain medical therapies. It sticks around long enough to do its job, but not so long that the patient stays radioactive for months. So how is lutetium-177 used to save lives? Well, the key is to make it highly selective, to get those radiation-emitting lutetium atoms to the diseased cells, like cancer cells, and nowhere else if possible. Enter the field of targeted radionuclide therapy. Scientists attach lutetium-177 to special molecules, usually proteins or peptides, that have a knack for finding particular cancer cells. It's a bit like attaching a microscoped homing missile to a radiation source. The cancer cells invite the molecule in, often because they have specific receptors on their surface that the molecule binds to, and lutetium-177 delivers a deadly dose of radiation right to the tumor, sparing most of the healthy tissue. One breakthrough example of this treatment for certain types of neuroendocrine tumors, rare cancers that can occur in organs like the pancreas or intestines. These tumors often have receptors for a hormone called somatostatin. Researchers developed a molecule, a somatostatin analog, that seeks out those receptors, and they labeled it with lutetium-177. The resulting drug, known by the tongue-twisting name of lutetium dotatate, commercially Lutathera, was approved for use in 2018. It's essentially a lutetium-guided smart bomb for tumors. When injected into a patient, the lutetium-177 dotatate finds the tumor cells and delivered localized radiation, Patients who had little hope with conventional therapies suddenly had a new option, and many saw their tumors shrink or their disease slow down. It was a real game changer in treating these rare cancers, extending patients' lives and easing symptoms. Lutetium, the obscure rare earth, became a lifesaver for them. Another exciting application is in treating advanced prostate cancer. Prostate cancer cells, especially when they have spread and become hard to control, often overproduce a certain signal on their surface called PSMA. Now, scientists created a small molecule that binds tightly to PSMA and hitched lutetium-177 to it. The result, popularly known by the brand name Pluvicto, was approved in 2022 for treating metastatic prostate cancer that no longer responds to any other treatments. In clinical trials, this lutetium-based therapy helped many patients by reducing tumor size and improving survival. Think about that. For patients who had exhausted the standard treatments, an element virtually nobody encountered in daily life offered fresh hope. Beyond these, lutetium-177 is used for palliative treatments as well. For instance, it can be attached to compounds that target bone tissues to deliver radiation to bone metastasis, cancer that has spread to the bones, and relieve pain in patients with widespread cancer. It is currently also being researched in other cancers, essentially anywhere where there is a targetable molecule on a tumor. Scientists are curious if lutetium-177 can be deployed to attack it. What makes lutetium-177 so well suited for these therapies is not just its half-life, but also the type of radiation it emits. The beta particles it releases can travel a couple of millimeters in tissue, enough to kill the tumor cell and a few neighboring cells, in case the tumor isn't perfectly targeted, but generally not far enough to blast distant healthy cells. The gamma rays it emits can escape the body and be detected by scanners, which means doctors can actually image where the lutetium is going, a helpful way to verify that the treatment is hitting the right spots. After a few weeks, the lutetium decays into stable form of hafnium and is no longer radioactive in the body. It is worth taking a moment to marvel at this. A metal that originally was only known to a handful of chemists is now at the forefront of modern cancer therapy. People who have never heard of lutetium are nonetheless benefiting from it when they undergo these treatments. In a very real sense, lutetium is saving lives quietly. It doesn't get the spotlight like iron in our blood or calcium in our bones or even iodine in our diet. But when it comes to these medical battles, lutetium is a hidden champion. It's amazing how lutetium transformed from a laboratory curiosity to a critical compound in advanced technology and medicine. For decades after its discovery, lutetium had no obvious use. Chemists studied it for the sake of knowledge, but there was little practical demand. It was simply too rare and too expensive, with only trivial applications, like maybe coloring lenses or as a research catalyst. Some may have even labeled it as a scientific collectible. Nice to have on the periodic table shelf, but not much to do with it. Now, lutetium is still a scarce resource, and that's unlikely to change. There is only so much of it in the Earth's crust, and it's hard to isolate. This means we will probably continue to reserve it for missions of high importance, where no substitute will do. Researchers are continually finding clever ways to recycle and optimize rare materials, so lutetium used, for example, in a PET scanner crystal or as a catalyst, is used sparingly and effectively. There is also ongoing research into creating lutetium-177 more effectively in nuclear reactors, and even investing cyclotron production to meet the growing medical demand without depending on large reactors alone. So we might see lutetium pop up in scientific headlines if those atomic clocks prove to set new records, or if new therapies emerge. Perhaps one day lutetium could be part of quantum computing components or new materials. Who knows? One thing is certain, lutetium will remain a low key. It's not going to become a household name or a common commodity, simply by virtue of its rarity and specialized uses. From the depths of rare earth ores to the front line of medicine, Lutetium's journey is a fascinating tale of how human curiosity and ingenuity can uncover immense value in the smallest quantities of matter. In a way, Lutetium teaches us that sometimes big heroes come in small, hidden packages. And so, while you might not wear lutetium jewelry or build bridges out of lutetium, this rare metal, this quietly brilliant element, is out there making our lives better bit by bit, scan by scan and cure by cure. Not bad for something you never heard of, right? Now, if you think I missed anything, let me know in the comments, and if you want to see another lanthanide, make sure to watch this video about yttrium next.